In the last video, we got a really nice way of thinking about the general solution to a homogeneous differential equation, like this one, with constant coefficients. That general solution is some constant times e to the r1x, where r1 and r2 are the two solutions to our differential equation's characteristic equation, the characteristic equation being this one right here, ar squared plus br plus c equals 0. And this is all plus c2 times e to the second characteristic solution equation, or characteristic equation solution, r2x. This is the general solution, but let's see what happens when we have an equation here where we have two solutions to the characteristic equation that don't give us linearly independent solutions to the differential equation. And if you remember, this is this one real root case where we don't have distinct roots. So that's going to be the subject of this video. Okay, I'm going to stop scrolling now so I don't nauseate you. If we have a differential equation like that, and let me just box some of this off so you get an idea of what we're working with. So let's box off an area for us with this new straight line tool that I learned. Let's say we have the differential equation y double prime plus 2y prime minus y equals 0. If we had this differential equation using our characteristic equation as r squared plus 2r minus 1 equals 0, we get that r is equal to, and we factor it out, so I guess we'll do the factoring down here. So it's just going to be r minus 1 squared, and okay, I am making up these on the fly. This should actually be a minus 2 if I want to make it r minus 1 squared. Alright, so this is r squared minus 2r minus 1, and this implies that r1 equals 1, and r2 also equals 1. And okay, if we just keep going, kind of keep our eyes on the ground, don't really worry that these are looking a bit fishy here, what we'll get is that our general solution should be equal to some constant times e to, okay, first root x plus some other constant c2 times e to, okay, second root. I'm just going to put 1x2, I guess. Yeah, this is a solution, we say, but it's actually not. And let's see why. Because if we remember, for any second order differential equation, we need 2 degrees of freedom, 2 parameters, 2 constants. And artificially, it might look like we have 2. Hey, we have c1, we have c2, we have so many constants, but we can factor out the e to the x. We say e to the x times c1 plus c2. And then c1 and c2 are just arbitrary constants. Their sum is going to be an arbitrary constant. So we get that this equals some new constant, c3 times e to the x. And now we're in a sticky spot, because now we only have one constant, one parameter, multiplying into our solution. So this is not so much a general solution as it is just a particular solution, any one solution. So this cannot be a general solution, unfortunately. But we can be crafty. We can make another solution, just as we made solutions for our homogeneous case with distinct roots. So I'm going to pitch a new trial solution to you, and we're going to show together that it actually is a solution, and then we'll use it to construct our actual general solution to the case where we have what is known as a double root. So this is, by the way, the double root case. Double root. Because we have this double root, there's only one. It has multiplicity 2. All those different words. Okay. So, how can we be crafty? How can we be sneaky here and make another solution to the differential equation? Well, what we're going to do is say, alright, we need our two solutions. This is y1. We need our second solution to be linearly independent of the first solution. So we're not going to be able to use another power of e on its own. But maybe we could modify it in the slightest way possible, just enough to make it so that it's not linearly independent. Sorry, not linearly dependent, that it is linearly independent. Just enough so it's linearly independent, but not so much that it isn't a solution anymore. So, what could that be? Let's just pretend we took x times e to the rx. How would this behave if we plugged it into our s equation? So my question is, what is, if we remember our operator s, which is essentially just our differential equation, how would s behave if we plugged in y2? Well, it's going to ask for a times y2 double prime, so I'm going to just leave some parentheses open there, plus b times y2 prime, and okay, we can actually calculate that. We're going to need to use the product rule, so first I'll differentiate the x, so we get derivative of x is 1, and then not differentiate this, so we're just going to get e to the rx. And now I'm going to differentiate the e to the rx, and I'm going to get x times e to the rx. You take the r down because of the chain rule. X times r e to the xr, I don't know what I'm doing there, rx. And then plus c times x e to the rx. Nothing changes when you don't differentiate. And if this is actually a solution, this should also be equaling 0, right? So we're just checking to be sure that this kind of weird solution, that it might work. Okay. And now let's plug in this second derivative. So the e to the rx stays the same when you differentiate it. And now notice we have x r e to the rx. If we pretended this r wasn't here because it's a constant and we're taking a derivative, we have another x e to the rx. And do we know how to take the derivative of that? We do. So now we can say this is plus r times, we're factoring the r out of the derivative, another e to the rx plus another x r e to the rx. Now I'm just factoring out the r from the derivative and then plugging in this right there. And now what we can do is expand this out. We'll get a times e to the rx plus r e to the rx plus r squared x e to the rx plus b times, and there's nothing special to do here, just rewrite it, x e to the rx plus cx e to the rx. And this should really equal 0 if it's a solution to our differential equation. So now, let's scroll down a little bit here. You might notice, okay, we have an e to the rx here multiplying into every term. So we could factor it out, but what would happen immediately is if this has to equal 0, e to the rx will never equal 0. Again, exponentials never equal 0 because you graph them. They'll just go very close to 0 and then up a lot, and this should be straight. So okay, the exponential is never 0, so we could factor it out, but then we'd immediately just take it away anyway because we want this to equal 0. So what we can do is we can just say, alright, this e to the rx, it doesn't really matter. Just factoring it out and getting rid of it. Okay, if we rewrite the equation, one more time, whoa, I'm green for some reason. If we rewrite the equation, now we equal a times 1 plus r plus xr squared plus b times 1 plus x plus c times x. And I think I forgot the r here, so pretend we're also multiplying in an r here. So this is actually not 1 plus x, but 1 plus x times r plus c times x, and this equals 0. And now this is in really interesting form. Even though we had this kind of weird second solution that we're trialing, it's starting to really simplify. Now, let's do one more thing, and let's factor out an x. Let's gather up all the terms with an x and all the terms without an x. If we take out all the terms with an x, we're left with this equaling, and I'll use colors to make it clear, x times, let me actually make this neat, x times, and we have a times r squared, plus, and now we have b times r plus b times r, and then c times nothing, just 1, plus, and now we have the second part, which is all of the not r's. So now we have a, which is right here, plus ar, which is this one, plus b, which is that, and that's just about it, and this all equals 0. And now what we get is, notice, ar squared plus br plus c. We chose r to be a solution up here. We chose r to be a solution of our characteristic equation. So it is necessarily true that ar squared plus br plus c equals 0. This must equal 0 by definition of r. So what we're left with is that this kind of strange solution is definitely a solution if a plus ar plus b equals 0. And okay, I have been actually carrying a slight error here. So when we took this first derivative, e to the rx term, I should have differentiated again to get r e to the rx. So let's just pretend that there was an r there the whole time. And if there was an r there the whole time, this is actually ar. So this is ar, which means that we actually get, and this makes a lot more sense to me, it was kind of confusing, that 2ar plus b equals 0. Okay, back to the drama. If this equation is true always, then this strange solution will be a true bona fide solution to the differential equation. But let's think back to what r is. Because r is a double root, we know this because this is the only case when we even need to do this. R is a double root, and that means that the b squared minus 4ac term of the quadratic equation equals 0. So if we look back to r's form, we get that r is equal to negative b plus or minus the square root of, well, okay, this is all just 0, divided by 2a. If this plus or minus is just for a 0, we can just get rid of it. We get this is minus b over 2a. And indeed, what we get here, if we plug in r equals minus b divided by 2a, and maybe you can see where this is going, is 2a times minus b over 2a plus b equals 0. We get that this equation is a solution, this function is a solution, if negative b plus b, canceling out these a's, if that equals 0. And negative b plus b always equals 0. So we end up getting this really nice cancellation for this almost, it's a simple manipulation of our original solution, but it's not one that you might expect out of the blue. But we indeed prove that if you plug it in, it is a valid solution because r is a double root. So what we get in the end is that a second solution to a homogeneous constant coefficient second order differential equation, I was just stuttering to remember my adjectives, a second solution on top of some constant times e to the rx is x e to the rx, which tells us, and we're going to have to kind of write it all the way down here, that a general solution, so I'll write it right here, a general solution to the double root case is some constant times e to your only rx plus some other constant times your actual variable x times e to the rx. This is only valid in the case that you're working with a double root, but it's still kind of cool, and you can indeed show x e to the rx, e to the rx, they are linearly independent, so this is a totally valid solution to the differential equation. Oh yeah, straight lines for a box. I'll see you in the next video.